Okay. Let me check everything's fine. The stream, let me check. Um, okay, I think we should be okay. Hang on, I need there we go. Okay. So this is now going to be A-level maths revision for paper 2. So obviously paper 1 was today's Friday, so it was Wednesday. No, today is Thursday. Thursday. So yesterday. And what I've done now is obviously I've seen the paper, I've seen the questions, and what the aim is now and today is to look at the questions that haven't come up, the topics that haven't come up, the questions, the sort of questions that come up that didn't come up, so for paper 2. And actually, where was it? And so the topics I predict will come up, although I don't think is anything special. But because of what came with paper 1, I think this will be in paper 2. So binomial expansion, some sort of like differentiation. There'll be lots of differentiation, I reckon. And I think quotient rule, implicit differentiation, parametric and differentiation. And like maybe a tricky differentiation one as well. I'm not sure. And then there's some parametric work again with differentiation or just normal stuff like finding combining an equation to get y in terms of x and stuff like that. Proof by contradiction, partial fractions, differential equations. I don't think there'll be a lot of integration in the next paper, but I think integration will come up with differential equations, and maybe integration with partial fractions. Combine the two together. There'll be some function work, so stuff like finding inverse, composition, the range and domain, all that sort of stuff. Modulus, so to sketch a modulus or solve a modulus equation, stuff like that. Some more sequences and series. Obviously, there was arithmetic, but there wasn't a lot to it. So I'd expect geometric and recurrent stuff to come up as well. Trapezium rule, potentially logarithms. So using the log rules, equations, making and solving equations with logs, and logarithmic model questions. And then some trig modeling, harmonic stuff as well, potentially. And then quadratic modeling and potentially straight line modeling. But I think that kind of came up in paper 1. But those are the, what was it, 13 topics I reckon will come up. So you could there or about make a paper out of it. Okay, so that's what I've done. So based on those topics, I've essentially looked at the past papers and got the questions from there, and that's what we're going to do today. Look at some questions here. If I probably won't have time to do all of it. It's 103 marks worth of questions. It'll be next time. So uh, I think I should stream today. Well, today and then when's the next day? Monday and then Wednesday. Obviously, Wednesday will be the night before. So there should be 3 sessions. I think this is going to be the first one. So if I don't do all of this now, it'll be in the Monday session. And yeah, that's really the plan. Also, it probably isn't a bad idea, especially to look at paper 2 in June 2022. And actually, October 2020, paper 1, because these 2 papers they have a lot of the topics that haven't come up in paper 1, that have come up in paper 1. So they have a lot of the other questions, right? These two would be really good to practice. But really, again, ideally, you should practice everything. You should practice as many past papers as you can. But yeah, particularly during 2022, because actually, I did it. I looked at the yesterday's paper side by side with paper one from June 2022, and they're basically identical. I think the examiners got very, very lazy. So that's not a bad idea. But don't expect paper June 2020. Don't expect paper two from June 2022 to be like this. Okay, the examiners will probably know people will cotton on to the similarity. They won't make it that predictable. Well, I hope not. But these two papers were really good practice. And I've went over 2022 paper two as well recently. If you check my past paper playlist. But yeah, um, and I've also picked some questions from here there as well, which we're going over today. Obviously, this one, the first one, is from that paper. But yeah, that's really it essentially. Guess we'll get started. Okay, so question one. Oh, here we are. Question one. Is a sort of generic recurrence relation question. So recurrence relation looks like this, right? So we have terms defined by the previous term. So here, this will do the previous term, and then we use it to get the next, and then that would be that you substitute back in to get the next term after that, and so on and so on. And we have to have a starting number as well for that to work. That's all it is really. Okay, so we have the sequence. We need to show that it's periodic and to state the order. Okay, so periodic makes like with a sine graph, periodic means it repeats itself. But to find that out, really, and with any sequence of series that is a bit unfamiliar, just work out the first few terms, right? So we already have A1 is 3. Then the next term, A2, well, if we use it, it's going to be 8 minus A1, which is going to be 8 minus 3, and that'll be 5. Then let's have a look at A3. So then that'll be 8 minus A2, which should be 8 minus 5, and that will get you 3. And then just we can check the next one maybe. A4 will be 8 minus A3, which should be 8 minus 3, which should be 5. And hopefully you spot there's a pattern, right? It's alternating between 3 and 5. So that means it's periodic because it's returning back to the same numbers. So therefore, sequence is periodic as it alternates between the same numbers, right? The same terms, the same numbers, right? Which are 3 and 5. Okay, that sort of thing. To justify it. And that's what it means, right? Periodic. Like with sine wave, the period and the cos wave is 2 pi, right? Every 2 pi, it repeats its same shape. Okay, the same sort of idea here. It's periodic because it repeats the same numbers, the same terms. So it's periodic in that sense. Okay, and then II, the order. Well, the order is basically just saying how many terms there are in the sequence. So kind of like how the sine wave is periodic. The period would be 2 pi, right? That's telling you the amount you between the starting point and then when it next repeats itself. That's essentially the same idea here. So as our first term is 3, how many terms until it repeats itself? Well, we have 3, then we have 5, and then we have 3. So actually it's 2 terms. So the order would be 2. Okay. So essentially in a periodic sequence, the order is how many numbers there are, right? Because then after you have that amount of numbers, 3 and 5, then it repeats back to itself. So the order there would be 2. Okay. Cool. Then part B is we need to find the value of this little summation here, 85 an, between n is 1. Okay. And you need to recognize what this sort of summation. This it's called sigma notation, and what that's saying is really from if you substitute n is 1 and n is 2, n is 3 to 85. you're summing A1, add A2, add A3, add A4, and so on till the last term A85. Okay, so hopefully you realise that. So we're just replacing n for 1, 2, 3, 4 to 85, and we're adding them because this little shape here means sum. So it's the series, so you're adding the terms. Okay. So again, like I said before, the best thing then with an unfamiliar sort of series is just add the first few terms, right? Let's see what happens. So remember, A1 was 3, then we got 5, then we have 3, then we have 5, and then it goes on, and then we have the last term, A85. Okay, I'm maybe not too sure what it is yet, but that's fine. Let's leave it there. Hopefully you recognise we have a patterns of 3 and 5s. And so essentially we're going to be adding some lots of 3 and some lots of 5. Okay, how... Obviously you might recognise this, but how are we going to split the series, or how are we going to work it out? Well, you could maybe think we do 2 of each, right? Because it's 2 numbers, so we say 2 lots of 33 and 2 lots of 5. Well, not 2 lots, sorry. There'd be there'd be equal amounts of 3 and 5, right? Because it's only 2 terms. But the problem is, if we divide 85 by 2, which is how many terms there are, you get a decimal. So it's a bit awkward. So it's a bit hard to see how to split it. However, what we can instead say is, what if we consider this to then make an even number? What if we add the first 84 terms and then add the last term by itself? Hopefully you can see that, because this is saying between 1 and 84. And then we have the last term A85, and that's exact same as this. And now this makes our life a lot easier because 84 is an even number. So what that is saying is now we can now split the 3 and 5s, because there's 2 of these numbers, into 2. So we can exactly say, well, what's 84 divided by 2? If we're going to split this up in 2s, what's the half of 84? Well, it's going to be 42, right? So then what we can say is, well, it'd be 42 lots of 3s and 42 lots of 5s, and then we have this A85 left over. Okay, so then really the last sort of mission is to find A85. So for that, you just got to recognize the sort of pattern that's going on with the series, right? Well, I'm going to list it again. So A1 is 3, A2 is 5, A3 is 3, A4 is 5, and so on. What do you notice between the n, the 1, the 2, and the 3, and what the number is? And hopefully you realise if n is odd, we get 3, and n is even, we get 5. So actually, 85 is odd, so that's going to be 3, right? If you think about the pattern. So then you just put that into the calculator, and then we get our result. 42 lots of 3 add 42 lots of 5 add 3 is 339, and that should be your result. Okay, and in general, this is a really good trick with series and recurrence relations to help you really visualize and see how to split the sum up when you have an awkward number like 85 here. So I guess as another example, say if we had the series 3, 5, 11. I think it's the same one last time, but 3, 5, 11 then goes back to 3, 5, and 11, and so on. And say if we had to add the 99, well, no, that's weird. The 100 series, right? The first 100 terms of AN, where A1 was 3, 5, and 11, and 3, 5, 11. Well, you can't exactly say it's well, it's like the 33 lots of 3, 33 lots of 5, 33 lots of 11 and stuff like that, because there's 100 terms. That's not divisible by 3. So really what you could do is with this sort of thing, well, how can we get this number down to make it a multiple of 3, which means we can evenly divide all these 3 terms by 3. And I think 99, right? Because 99's divisible by 3. And then I can add the last term, which is A100 here. Well, 99 is divided by 333. So that means when I do that, it's going to be 33 lots of 3, add 5, add 11. And then we have this last term here. Well, I noticed, well, A99 was the term before it. That's a multiple 3. If I also notice the third number, the third term and the sixth term is 11. So therefore, the 99th term, which is also multiple 3, I can clearly see in multiple 3s, right, is going to be 11. So that means this also is going to be 11, right? If you think about the pattern. So that means the next term is going to be 3, because obviously 11 then goes to 3. So that would be 3, and then you put that into a calculator, you get this series here. If you add all the first 100 terms in this series. So that sort of idea of splitting up. When again, if you have an awkward number that doesn't quite split all the numbers you have up nicely, go back a few terms to then get a number that is nice, like 99, which can divide by the 3 numbers, and then you just add on the last term or so, and then hopefully you can work out what this term is. It's a lot easier than trying to really like faff about. I don't know. I find that's one approach anyway. Obviously, if you have your own, that's cool. But that's one way you can approach this sort of series without much mess. But yeah, okay, that's that question. Cool. Question 2. Again, this is on page June 2022, paper 2. So we have these values for x and y, and we need to use the trapezium rule to estimate this integral here. So this formula, in the formula book, you are given the trapezium rule. I've copied and pasted it here exactly, and that's going to be crucial, right? So really, you got to recognize how to use it, right? But you are given it, and really, if you know how to interpret it, and I'll go over how to use it now. But if you know how to use it, it's actually pretty simple. So before you use the formula, you're going to need to work out this h. And this h is given here. So if we have the integral, part A, the integral between 9 and 3 of log 3 to the 2x. Well, first of all, your b minus a, those are your up and the lower limits. So that means your h is going to be between 9 and 3, which should be 9 minus 3. And then you have your n, so that'd be 6 over n. Now, the n's probably the trickiest bit, but this is where you use the formula to guide you. So the n is referring to the number of strips, so the number of trapeziums in the trapezium rule. So if our graphs say look like this, if we have 1, 2, 3, 4, 5 points, it's going to be like first point, second point, third point, fourth point, and the fifth point. So actually, how many trapeziums we've got? 1, 2, 3, 4. So actually, n, the number of trapeziums or strips, is going to be 4. But how would you kind of get that without, kind of considering the geometry, right? And that's where this formula comes in. So notice what this is doing here. So these are adding all the y values of our points, which are here. But notice it starts at y0, and then it goes to y1, y2, and then yn minus 1, and then yn at the end. So that would mean that has to be y0, and then that would be y1, y2, y3, and then y4. So actually, by counting like that, you can then deduce n, the final bit, has to be 4, which is what we got here. So again, use the formula to guide you if you're not unsure about what the n is. I think the n, deciding what the n is, probably the trickiest bit, I feel like. But once you got that, well, we found our h value. So 6 over 4, again, is what, 3 over 2. Seeing this after being out of uni over a year now, suddenly flashbacks to simpler time. Oh, I know, I know. I've been the same. I've been out of uni for, when was it now? About 5 years and that. No, 5 years, sorry, 3 years. Haven't done any maths since, until like a few weeks ago, really. But I thought I'd managed to do some A-level stuff to help people out for the exams. But you know, I'm getting to grips with it a little bit as well. But I don't know. I kind of get most of it though still. But yeah. Anyway, so we have a H now, so we've got all our ingredients right to find this area here by the trapezium rule. So if you just apply the formula, that's going to say the integral is going to be a half of H, half of 3/2, times by this whole bracket here of y0. Right, again, y0 is our first y value, so it's going to be 1.63. And then the final y value, which is 2.63. And then we have to add two lots of y1, y2, and then and then the term before it. So the other values, right? So two lots of 2, add 2.6, and then 2.46. And then that's really just a job for the calculator, right? So put that into the calculator. Be half of 3/2. 1.63, 2.63, and two lots of 2, add 2.6, 2.46. And that should get you this result here. Hang on. 2757 over 200. And you put that as decimal if you want, that's completely fine. As a decimal, that would be 13.785. But obviously, A level, we love fractions, right? Just leave it there. Okay, so that's the result. Cool. Centripedes involve having to prove n is real and non-infinite. Makes life so much easier. Yeah, like numerical analysis. Yeah. Always have to consider like the error bounds, stuff like that. Oh god, that takes me back. Okay. So part B then, we have to use that answer to part A to estimate these interval inequalities, right? These inequalities, what's that? Integrals. So 9 of 3 of log 3 to the 2x to the 10. And hopefully what you recognize here, these are logs and the logs, so we have to use log rules, right? And so really there's two main ones. It's going to be like a power one, right? Power one, so it's going to be a to the m. It's going to be like all n. That's probably what most people use. N log a, and then we've got the addition one. So if we add two together, and obviously there's a subtraction one as well. But let's just consider this one first. Okay, so which of these two is most likely? Well, we have a index staring at us, right? So I think we're going to have to apply the index one. So we bring the power to the front. So it's going to be the integral between 9 and 3 of 10 log 3 to the 2x. And what do I notice here? Well, I can bring the 10 out. And then what do I notice? It's the exact same integral we had in part A. So that'd be 10 lots of our answer. So it's going to be 10 lots of this fraction here. Which would be 2757 over 0. Well, that'd be over 20, right? And that's the sort of thing, right? So it's a fairly common sort of exam question to use log rules to simplify stuff, and this will it will come up in paper too. And they might combine it again with trapezium rule or something. So yeah, it's okay. It all tends to about 3 by real analysis. Oh, okay. I don't know. I can't remember that far back now. uh, um. Okay, so we have part II, and now we have to somehow find something with this interval. So 9 and 3 of log 3 to the 18x dx. Okay, so again, that goes back to the two sort of log rules, right? Do we have a power? Well, not really, no. There's no power here. So the only other way we can kind of do something with this is by somehow forming a product. And I recognise we have a product here of 18 and x. But I need the 18x to go to a 2x, right? In order to then use our original integral. Well, how are we going to get 18x to 2x? Well, I reckon it'd be 2x times 9, right? So then I could say that's between 9 and 3 of log 3 of 2x times 9 dx. Um, and then we split this up, right, using the integral. So that's between 9 and 3 of log 3 to the 2x add log 3 to the 9 dx. And so what I notice now, again, I can split this into two different integrals because they're adding. So it'd be 9 3 of log 3 to the 2x add the integral between 9 and 3 of log 3 to the 9 dx. Now, actually, this integral again is what we had in part A again. So that's the whole idea, right? Keeping part A in mind, try and get that what did you call inequality? Integral, uh, and then that's what we got here. So actually, this is our part A answer again. So that's going to be 2757 over 200. But actually, this although looks a bit nasty, it's just a constant, right? Because these are all definite numbers, log 3 to the 9. You can actually put that into the calculator if you wanted, but really recognise that log 3 to the 9, although you don't have, again, you can put that into the calculator, but that will be 3 squared, right? And then I can bring the 2 out, and then log 3 to the 3 just goes to 1, so then 2 times 1 will be left with 2 dx. If you are a bit, if you feel a bit weird dealing with logs like this, you can just put that into the calculator. If you know it's a number, obviously you're not too sure what to do with it, it's fine to just put it in the calculator, really. But that's the step, right? Anyway, so that's between 9 and 3, 2 dx, and actually we know how to integrate this very nicely, right? So that's going to be 2757 over 200, and now that would be 2x, right? And it's between 9 and 3. And then if we evaluate that, 2725 over 200, add 2 of 9 minus 2 of 3. So remember, they substitute the upper limit and then subtract by the lower limit. And they put that into the calculator. You get this number here, this fraction here. 5157 over 200. That's it, right, for that question. So hopefully you can start to see there how you sort of apply the log rule to simplify stuff, which again will be a very important skill, I reckon, for paper 2. Um, so yeah, hopefully that made sense, hopefully. So yeah, I guess the main takeaway is, again, for A, use the formula to help you find an n here, the number strips. So you know the first point has to be y0. Then you can count up to find the last point, which is y4. That means n has to be 4, because obviously the final point here is n. Okay. And as for the log rules, if you have an exponent, like I said, that should be fairly clear when you use an exponent. But if there's no exponent involved, then you're probably gonna have to make some sort of product, right? Or division or something, to then simplify stuff. But okay, hopefully it made sense. I'm gonna move on now. Question 3. Cool. Oh, uh, and I reckon this could happen, right? So we have a differential equation mixed with partial fractions. So I reckon that probably could come up. So let's have a look at it. So part A, express 3 over 2x minus 1, x plus 1 as a partial fraction. Well, that means essentially a partial fraction. Hopefully, you practice this. You're splitting up each into like a separate, a linear denominator. So denominator of only one factor, right? So the whole idea is you factorize it, and then you split up all the factors into different fractions. That's essentially what's going on. So we have a over 2x plus 1 plus b over x plus 1. Okay, and let's make it a bit clearer. Okay, so I need to find a and b. I reckon, let's try and add it. So ax plus 1 plus b 2x minus 1. So I'm just adding the fractions together to get common denominator, which again will be x plus 1, 2x minus 1. And I noticed this is in the exact same form as the original fraction, but the denominator is the same. So that means the numerator also has to be the same, which means we get this. And now this is essentially some sort of simultaneous equation, and you can do this many ways, right, to find a and b. I think perhaps the best way is to set each bracket equal to 0, because what that will ensure is that you get rid of all the constants, right? So you only have one equation with one constant. That's easy to solve, right? So the first one, let's let this bracket equal to 0. So that's going to be x plus 1 equals 0, so x will be minus 1. So we sub that in. My 3 is just going to be 3 still. And 3 will be a lots of 0, which will just be 0. And then b of 2 lots of minus 1 and minus 1. That will be minus 3b. So therefore b would be, minus 3b is equal to 3. So b would be minus 1, right? Okay. And then we do the same for the other bracket. So 2x plus minus 1 has to be 0. So that means x has to be a half, right? So therefore 3 would be a lots of a half plus 1. And then plus b, well 2x minus 1 will go to 0, so that's nothing. And that would be a half plus 1, that would be 3 over 2a. Well then therefore a has to be 3 divided by 3 over 2, which should be 2, okay? And there we are. So now we found our values. So then as a partial fraction, what was it? The original fraction of 3 over 2x minus 1, x plus 1, is going to be a lots of 2x minus 1, was it? Let me double check. Yeah, a over 2x minus 1, so a was 2. And then add b, which would be, well, add minus 1 over x plus 1. But obviously the minus can be brought out, so it'd be minus 1 over x plus 1. And that's your partial fractions. Okay, cool. So part B, then we are given the big block of text. Don't get bogged down by the words, right? But really, all you got to factor it. The only thing that's really staring at me right at the moment is this differential equation here. And immediately I'm thinking, I'm probably going to need to solve this. And actually, I do. So really, I just need to solve this equation and ignore pretty much all the words, right? Perhaps no, not V and TR might help, but we can deal with that when we get to it, okay? So let's just solve it then, right? So we have dv over dt is 3v over 2t minus 1 t plus 1. And with A-level math anyway, we essentially separate all the variables, right? So that means one variable has to be on the one side, so we're going to have to times by dt, right? So that's the first step. dv is going to be 3v over 2t minus 1 t plus 1 of dt. That's always going to be the first step, right? Unless obviously you're very confident and you can do it all in one. But that's the first sort of approach. Getting rid of the dt. And so then I've this on one side and the other d on the other side. So I need to get all the variables as separation of variables hints. We need to get all the one variables, so the v has to be on this side, and all of the t's on the other. So we have 3v on here. So how are we going to get rid of v? Well, we're going to divide by v, aren't we? To get rid of the v on here. So therefore, divided by v, we'll get 1 over v dv. Obviously then, because 3v over v will cancel out. Okay. And then that'd be 3 over 2t minus 1 over t plus 1 dt. And now all the t's on the other side as well. Cool. And so because we have this dv stuff here and this dt, that means we can integrate. Because obviously an integral has that dx bit at the end. We already have that d bit, so we can actually just integrate both sides. So 1 over v dv is the integral. I'm going to bring the 3 out, actually. I don't like having multiples in my integrals. I don't know. But that'd be 1 over 2t minus 1 over t plus 1 dt. And so actually, I should now be able to integrate both of them. Well, 1 over v is sort of like the reverse chain rule, or like the log rule, essentially. So 1 over v will be, the integral will be ln of mod v. Okay. Pay attention to the modulus here, because v could be negative or vice versa, with the t or whatever. But it has to be a modulus, because obviously logs aren't defined for negative, so we have to account for that. Okay, because our original function, right, our original value of v is not modulus, right? It could be a minus, and that'd be fine. So then if we then do some integration, we have to account for that possibility by adding a modulus. But don't worry about that too much. You just need to know we have to have a mod v. The reason for that, very briefly as well, is because this reverse chain rule sort of situation here. So if we have the f of x and we have f dash of x and some lots of it on the top, if this differentiates, v differentiates to 1, doesn't it? So actually, then the integral will be the log of the bottom function, which should be v, and that'd be mod v. So that's briefly where that comes from, right? But yeah, that should be. I hope you practice stuff like that now. Anyway, hopefully that should be too bothersome. So then we have 3 lots of this, and actually, I don't really know what to do here. Obviously, hopefully you should spot it though. But I know this split up to partial fractions because, like I said earlier, we have factors in the denominator, so that means we can split it up, and that's what we've done in part A, right? We have this expression here. So 3 lots of 2x minus 1 is this. So if I just bring the 3 back into here, say, that's exactly the fraction we split up into partial fractions, right? So then we can say 3 lots, or all of this is these 2 fractions here. So we just substitute that in. So we're going to have 2 over 2t minus 1 add, no, it's minus, wasn't it? Minus 1 lots of t add 1 dt. Okay. Oh, no, that should be in t's as well, not x's, sorry. T plus 1 t is 2t minus 1 t. There we go, not x's. Okay. But then in the same sort of principle, I can then use the log, it depends what you call it, reverse chain rule, log rule. So I recognise 2t minus 1 differentiates to 2. So actually it becomes, so ln v equals, and this becomes log or ln of mod 2t minus 1 minus, and then t plus 1 differentiates to 1, which is exactly what we got. So it's exactly ln of t plus 1. And there will be a plus c, right? Because it's indefinite integration. There's no limits on any integral. So we need to account for plus c. Okay. What I then know is I can bring the logs in together. So 2t minus 1 over t add 1, because we have this minus here. So again, remember the log rule, log a minus log b equals log a minus b. I might not be able to do anything with that, but it's staring at me in the face, and maybe it'd be useful. So I'm going to do that, plus c, okay? Okay, now to find plus c, I believe we are given some information. So it's exactly 2 hours. T's in hours, right? So that means T equals 2. Total volume of 3 of oxygen. Well, V, where's V? The total volume of oxygen produced is V. So actually V then would just be 3. And so we're going to solve it, right? So then we're going to say T is 2, V is 3. Then we're going to substitute that in to then find C. Okay. I'm not gonna. You could try and not make it a lot more presentable to then get V on its own instead of log V, but then have this plus C, so it makes it a bit fiddly. I think I can find C straight away, right? So V is 3. That means log 3. So mod 3 is obviously just 3. It's gonna be log of 2 lots of 2 minus 1. Let's make it over 2 add 1. So I'm substituting t's 2 in. So that means log 3 has to be log of 2 times 2 is 4 minus 1, which should be 3 over 3. That's going to be log 1. And then log 1, you can put that into the calculator, but it's going to be 0, right? So that would be 0 add c, which means c is simply ln 3. So then I can bring this back in to say ln v now has to be ln of 2t minus 1 over t add 1 plus c, which is ln 3. Now actually, again, I can use the other log rule, which multiplies them together. So log AB is log A add log B. So I've got two logs added together, I can bring them in. So then say ln mod V is ln of modulus of 2t minus 1 over t add 1 ln 3, 3, sorry, times 3. You can bring it in even though this one is 3 is not a modulus, because of the fact 3 is positive, right? So it wouldn't affect it at the end of the day. So you can do that, okay? And so that becomes ln of 2t minus 1. Rather, that'd be 6t minus 3, wouldn't it? Over t add 1. I just times 3 on the top bracket. And so that's equal to ln mod v. Well, then I can clearly see that the inside the logs have to be the same, right? So that means v has to be 6t minus 3 over t add 1. Cool. You may be... no, actually, never mind. And yeah, that's what we get, I think. Let's check what they wanted. Oh, it should be 3, apparently. Uh, Interesting. Okay, so I'm off by a factor of 2. So they got 3 lots of 2t minus 1. I got 6. Why is that? Oh no, that's the same. Of course it is. I've just expanded it. 3 2t minus 1 is 6t minus 3. Oh my god. There we go. I don't know why that's. Oh god. So therefore we could say that that's log of 3 lots of 2t minus 1, just to make it very clear, over t add 1. And then therefore the logs inside have been the same. So that means v is 3 lots of 2t minus 1 over t plus 1, which is what they got. Yes, okay, there we go. Lovely. Okay, then we're going to do part C. I'm going to do part C over here. I don't have much room. Then it says the scientists deduced there was a time delay between the chemicals being mixed and oxygen being produced. So remember, V is the oxygen produced. So if there is a time delay, that means that obviously V equals 0. And what's essentially going on there is if there's a time delay between oxygen being produced, that means when like V is 0, so here, right, that's V0. Um, there's like this little uh, delay before the V starts going up, right? Something like that. So that delay before the V starts jumping up or moving up or down or whatever, but it's going to go up, right, because it's volume. That is the time delay. And it says the limit. I'll talk about the limit in a second. So then it says on the time delay. So again, the time delay is when V is 0, because obviously there's no oxygen produced. So again, bear in mind V is 3 lots of 2t minus 1 over t add 1. We need V 0, right? Now when V is 0, obviously this whole fraction is equal to 0, right? Because that's V. Now, that means the numerator has to be 0, 3 lots of 2t minus 1. Again, if you're a bit unsure with the denominator, you could just times across. So 3 lots of 2t minus 1 is 0 lots of t add 1. But 0 lots of anything is just 0 still. So it's just the numerator equals to 0. Okay. But then 3 lots of 2t minus 1 equals 0. But then we could just divide by 3. So then 2t minus 1 equals 0, which means t is a half. So that would be our time delay, right? So it goes up to t is a half before it starts going up. Okay. Now t's in hours, so a half of an hour is 30 minutes. Okay. Yeah, it says give you answer in minutes, so yeah, I need to make sure of that. Then it says the limit, so it's talking about the limit to the total volume of oxygen produced. So that means no matter how long it takes, there'll be no more oxygen produced. That means we need to consider when t goes to infinity. Now, I did speak about this before, but I'm not a big fan of of this sort of thing in normal math because they don't really teach limits like that. But essentially, there's two ways you can do it. So again, V is this here. We need to see what happens when t goes to infinity. And it's not immediately obvious because there's a lot of t's on the top and the bottom, right? It's not immediately obvious where that goes. The one strategy you could is to plug in a very, very large value of t and see what happens there. Um, so you could say t is like a billion or something. So if I did like a billion, 3 lots of 2, so that'd be like t is 10 to the 9, wouldn't it? Um, it doesn't matter. We need a large value of t. So if we just plug in 10 to the 9, for example, or 10 to the 20, or whatever, some really large value. Um, 3 lots of 2 of 10 to the 9 minus 1 over 10 to the 9 plus 1. You get v is 5.999, and it really lots of nines, and it goes to an 8. So clearly that's going towards 6, right? And that would be your limit there. Okay, so v would be 6 is the limit. Okay, of oxygen produced. Which we can deduce from the fact it's very clearly tending towards that sort of number, right? 6. The other way, and the more formal way, is actually, well, if we expand the bracket, we're going to have v is 6t minus 3 over t add 1. Now, if we actually divide by t or times by 1 over t on both the top and the bottom, we're going to get 6 minus 3 over t add 1 over t. Now, what you do need to recognise is 1 over t, when t goes to infinity, this goes to 0. Right, and again, you can even say that with like a reciprocal graph. Let me scroll down. Reciprocal graph. So obviously, as t goes to infinity, 1 over t goes to 0. Or again, just try some numbers and see what happens when t is very large. When you recognise that, that means v alternatively, when t goes to infinity, that means 1 over t goes to 0, and then we can substitute that in to say that's going to be 6 minus 0, right? So 6 minus 0 over 1 plus 0 is 6. And that is your limit, okay? So that's the formal way of doing it. And hopefully that showed you. Hopefully it made sense. That's the proper way. But if you are struggling, stuff like that with limits, they don't teach it very well. So I don't think they make it too complicated. So you can just try and plug in some large values, right, see what happens. But yeah, so that's that question. So therefore, limit is 6 meters cubed. Cool. Okay, that's question 3. Um, so again, be prepared to like mix with partial fractions at other parts with differential equations and stuff like that. You never know. There might be a very similar question. This was from 2022 paper 2. So you never know, based on the trend from paper 1, there might be a very similar question. So hopefully now you've seen all like the different bits to it. Okay, we have question 4 now again from paper 2, 2022. And so we are given a function f, which is defined as this. We need to find f inverse of 3 over 2. Okay. Again, there's two ways to going about this. Recognize either x, y, if you the inverse function, then the coordinates would be yx. So y is like the input of f inverse. So f, and that's f inverse. Y can't, they switch roles, right? That's the whole idea of an inverse function. So what that's saying is, if that input's 3 over 2, y would be 3 over 2. Therefore, you're solving 8x plus 5 and 2x plus 3 equals 3 over 2. And then you find the value of x, right, that gets that. I'm going to do part A here, yes. Alternatively, and this is the way I'll do it, because I think a lot of people would be more comfortable in doing it this way, is to simplify the generic function f inverse using what you know by saying y is f of x, so y would be 8x plus 5 over 2x plus 3. Then you rearrange to get x in terms of y again, because they switch roles. So that means we have to rearrange to get x in terms of y instead. And that's your inverse, right? And then you can just plug in 3 over 2. Okay, let's do that. So again, so the first step really is to get rid of the fractions, so times by 2x plus 3. And that would be 8x plus 5. Let's then expand it. So 2xy plus 3y equals 8x. Add 5. And then I want x is on their own, so it's 2xy minus 8x is 5 minus 3y. Then I can factor an x out, say 2y minus 8 is 5 minus 3y, and therefore x is 5 minus 3y. 2y minus 8, I've now switched them around, so that means the inverse of x would be 5 minus 3x, not y, remember x, in terms of 2x minus 8. And then I can just say, to then find f inverse of 3 over 2, that will be then substituting 3 over 2 in. So it'd be 5 minus 3 of 3 over 2 over 2 of 3 over 2 minus 8, and that will get you minus a tenth. Okay. And then part B. Says now we need to show f of x can be expressed in this form here. And again, there's two ways of going about this. And either you could do it directly. So again, kind of like partial fractions. You could either just combine them together. So you could say that's a 2x plus 3 plus b over 2x plus 3. And so the numerator has to equal the numerator here because the denominator is the same. So that means a of 2x plus 3 plus b would equal ax plus 5. Then you do the normal sort of method, like partial fractions, like that we did earlier. You could substitute two values of x in to get a and b, or compare, or do whatever, and then you can find a and b that way. Alternatively, you should actually spot this is a top-heavy fraction because the degree of the numerator is at least the degree of the denominator. An algebraic fraction should always have a denominator of a higher degree of x. But here they're both degrees of 1 because it's a linear. So actually what that means is we should be applying long division here. So if we apply long division, that's saying 2x plus 3. And either method's fine, by the way. It's not like you only can only do one, right? The mark scheme will always award as long as it says, for example, if it said by using long division, you have to use long division. But if it doesn't specify any particular method, you can use any valid method, right? That gets you the answer, and you show your work, and you'll be fine. So either method or whatever else is fine. But then if we carry out this long division, 2x plus 3 of 8x plus 5, then we need a number that times by 2x to get 8x, right? So considering the first highest power of x, they need to match. So that would be 4, right? And then 4 times 2x is 8x. And then 4 times 3 is 12. And then we have to minus from each other. So then 8x minus 8x is 0. And then 5 minus 12 is minus 7. So therefore, that means the quotient, so f of x is that. And so the quotient be 4, and then the remainder is minus 7 over this 2x plus 3. And that means clearly a would be 4 and b is minus 7 here. Okay. But if we then compared it again, like we did earlier, if we then compared it if you did the comparison method where you added the fraction and then you looked at setting values as some values of x to 0 or whatever to match with the numerator here, you should get the same values of a and b. Okay. But yeah. Then we say part C. So what's part C saying? And then the function g is defined by g of x is 16 minus x squared between 0 and x and 4. State the range of g inverse. Okay, so immediate notice it's 1 mark and it says state. So that means we don't have to do any working really. So I should be able to just see it. Okay, so the range of, but it's saying the range of the inverse function, and we're given the original function. And what you should recognize is this is the same as the domain of the original of g of x, right? Again, the reason why that is because of the fact that x and y's switch, right? They switch roles when it's f and f, the normal function and the inverse function. So that means the domain of the original will go to the range of the inverse and vice versa. So then we just need the domain of g of x, but we are given the domain. This is it. It's the values of x we can use, right, at input. So actually, it's between 0 and 4, the range. So we can spot that the range is g inverse and between 4, not x. Yeah, it's the inverse function g of minus 1, okay? Then we have part D. Then it's asking for the range of fg minus 1. Now, you should recognize again, this is a composition. This is saying f of g inverse of x. So that means the domain of f, or the input of f, is actually the g inverse of x, okay? So then to work out the range, we need to work out what input f can take. But we already said that g inverse can only be between 0 and 4. So that means we need to consider f of x between 0, x, and 4, right? That's really the range between when x is 0 and 4. So then let's consider the endpoints then. So f of 0 and f of 4. So f of 0, so f of x, remember, is well, we worked it out in part B. It was 4 minus 7 over 2x plus 3. So then f of 0 then is going to be 4 minus 7 over 2 of 0 add 3, and that will be 5 over 3, right? Likewise, f of 4 would be 4 minus 7 over 2 of 4 add 3, and that would be 37 over 11. Cool. So then you'd probably be, and so that's cool. So it's between 0 and 4. So the last thing we need to check is if the function's increasing. So obviously 5 over 3 is smaller than 37 over 11. So say 5 over 3 is here for f, for our range for 0, and then at 4 it's 37 over 11. So it goes from here to say here. We need to check there's no turning points, or in other words, we need to verify that it's an increasing function, right? So that means there's no jumps like this, right? Because of a turning point, there's a value that goes out of the range between 5 over 3 and like 7 over 11, right? It if there's nothing that goes above 37 over 11, which would happen if there's a turning point, right? Or likewise, it could go beneath, or and stuff like that. The only way it can go like that is if it's increasing. So that means for every value of x, as x goes higher, the function always goes higher. So that essentially bounds it between 37 over 11 and 5 over 3. So we just need to see that it's increasing. If you were stuck, this is probably quite complicated, right? It's quite what's it, abstract to see this. If you were struggling, you'd probably just say f of 0 and f of 4, and then just put these as your values, right? So f of 5 over 3 between f of f g inverse, right? 37 over 11. Actually, that is the right answer. If you're either stuck, you can just do that, but you just also need to verify it's an increasing function, and you can see that because of part B. So remember, we defined our function to be 4 minus 7 over 2x plus, not to find it, sorry, we worked it out to be that, right, in part B. This means there's only one x there, which means there's only one place it varies. That helps us a lot because we can then just consider where it varies and then obviously work away from there. We don't have to consider like say like with originally in the original fraction there were x's in two places, so we kind of have to somehow like balance and like juggle the x varies in two places. It's a bit iffy. It's kind of like we complete the square, right? If you just had a normal quadratic, I don't know, like 2x squared and 3x plus 4, it's very hard to see what the maximum is because x varies twice. We can't just like, you know what I mean? But if you then complete the square, I don't know what the complete square form of it. It's like 2 of, what was it, x plus 3 over 4 squared. I don't know what the other. It's just and a constant. Okay. We can then clearly see because x varies only once. We can kind of like clearly see where the maximum and any turning points are. That's the same sort of idea here to see where the range will be. Okay. So part B is useful because we only have what again only one variation because there's only one x. So what that's saying is, well, let's consider what happens to x. So when x increases in general, as x gets bigger, 2x plus 3 gets bigger, right? Um, then, because we're divided by a bigger number, 7 over 2x plus 3, that means the fraction overall gets smaller, right? Because, again, we're dividing by a bigger number, the denominator gets bigger. But then we're subtracting by the fraction, right? And because all these numbers are fixed here, again, the only thing changing is the x. So as the denominator gets bigger, the whole fraction gets smaller, but we're subtracting by a fraction. So as the fractions get smaller, we're subtracting by a smaller number as x gets bigger. That means this whole function overall gets smaller as x gets bigger, sorry, as x gets bigger. Because we're subtracting by a smaller number, that means we're taking less off the 4. Okay, so that means that as x increases, uh, then the whole fraction gets smaller, so we subtract by a smaller number. So actually, we get a more positive answer, and so it's increasing. Okay, because of that sort of logic. Therefore, because it's increasing, it has to be between uh, the point 0 and 4, right? There's no weird jumps because of the fact we already considered it's increasing for all x, right? It doesn't go, if we had a maximum, right? For example, if it jumped up, that would say it would be going down at certain points as well. But it's not decreasing at all because of what we just discussed. It has to be always increasing, so it has to follow exactly this sort of shape. Okay, it has to be an increasing function because of that. Therefore, it has to be between 5 over 3 and 37 over 11, our two limits, right? So therefore, we can essentially prove and verify it is indeed 5 over 3 and 37 over 11. That's where the range is between. Okay, that is very, very complicated. You do not get any marks for that, by the way, for considering or proving it's increasing, but you do have to check it, right? But for A level, it's not going to be too bad. Again, like I said earlier, if you are unsure, just like write the inequality down, right? And you'll get most of the marks, right? Even if it's not that sort of way. Uh, but yeah, that I know that is very tricky. It's very analytical. You have to think very, very deeply about that, and that can throw a lot of students off. I am aware of that, but you do have to prove it. You have to basically rule out the fact there's no turning points. If there are no turning points, then that means there has to be an increase in function, right? To avoid the fact there's no jumps, right? And if there is a jump, that means it has to come up and then it has to come down. So it'd be decreasing at certain points. So we have to rule out the fact it doesn't decrease, essentially. Okay. I'm gonna leave that question there. Then hopefully that made some sort of sense. I know that's very complicated. Um, but yeah, the mark scheme just essentially jumps from f0 to f4 to this right inequality. Like I said, you get no marks for considering the fact it's increasing, but you do have to consider it, right? Um, but yeah, that's I know range is what a lot of people struggle with. I don't have much to say there, unfortunately. Other than I don't know. Other than it won't be too complicated. Hopefully, they'll be fairly simple with it. Okay, like I said here, you just plug in. In this case, all you have to do is really just plug in the two endpoints, and then there's your range. Okay, let's move on. Question 5. Cool. So this is logarithmic modeling. Because obviously we have a model given here, and it's with a log. Okay. And this could come up as well. Okay, so we'll let me scroll down actually. So we're given this graph, we're given 2 points, and we turn the value in pounds and in t in months. We're given this formula, this model, right? V is AB to the t, and it's a linear relationship between log V and t. It's linear, meaning it's a straight line, right? Then it says it passes through these 2 points, which we see on the graph. Then we need to find the initial value of the phone. So that's going to be when t is 0, and we need the value v, okay? Not log 10 of v, but v. So that if we plug in t, let me do part A then. Well, if t equals 0, then v is going to be a b to the 0, which is going to be a. But we don't know a, so we're going to have to work that out. But we know we know log 10 of v and t. We know that we can't substitute these points into here because this is log 10 of v. This is not v. Well, then we're going to kind of have to take logs then, right? So we're going to say then if v is ab to the t, therefore log 10 of v is going to be log 10 of ab to the t. And that's going to be always the way you tackle these questions. When you're given a log sort of model like this, if the graph's in logs, you're going to have to take logs on the equation, right? This is essentially linearizing the graph. And you can see because it's now linear. And that's the strategy. Always take logs of your equation if it's given in logs in the graph or the model. Okay, so now we can use log rules to separate this. So again, I know we can say it's log 10 of a add log 10 of b to the t. Hopefully you can see that right. That's just log rules. So if we have a product, again, we can split that up into an addition of two different logs, and I have a power of t. So now I can say that's t log 10 of b. Now I can substitute a point in, perhaps, to find a. And I'm going to substitute this point, I think, because we have a 0, so that's always going to be nice, right? So again, t is 0 now, so that means log 10 of v. Well, we know what log 10 of v is, don't we? We know that log 10 of v is 3, right? Because remember, this is this point here, and this point is on it's on log 10 of v. Okay. So that means log 10 of v is 3. Okay. Hopefully, the main point here is to recognise the distinction between v and log 10 of v, and why we cannot substitute these points into this equation. So we have to substitute it into this log equation instead. That's why we take logs, so we can substitute these points in. And then we can convert between log 10 and v by taking exponentials or logs or whatever. Okay, so now we have this. So then we can say no, log 10 of that's 3. That's going to be equal to log 10 of a, and then add t, which is 0, log 10 of b. But anything times 0 is 0, so that is all just log 10 of a. Well, we need to find a, but we can find a. Because then if we raise by power 10, that means 10 to the 3 is 10 to the log 10a. And they cancel because they're inverses, right? If you want to think of it that way. So that means a is simply 10 to the 3, which is 1,000, right? 1,000. Well, that's our value then. Therefore, the value v, not log 10 of v, but the value v, remember we discussed here the initial value v is a. That's going to be 1,000. Okay. Cool. Okay, hopefully that made sense. But yeah, I think that's probably the tricky thing here. Then part B. Then it says to find a complete equation for V here. So we have to find the missing values A and B. But we know what A is already. A is 1,000. So we just need to find B now. Well, we are given another point on this line here, aren't we? We are given another point that lies between log 10 and V and T. So I think we can use the equation we found in part A, right? So remember, if we take logs on both sides, log 10 of V is going to be log 10 of A, but A is 1,000. Now, if you remember, 10 cubed is A. So that means we could just move it to the front, so 3. So then log 10 of 10 is 1. So then you're left with 3 times 1 is 3. If you are unsure of that, just plug in log 10 of 1,000 in the calculator. You'll get 3, okay? If you are unsure about stuff like that, you do have to calculate to help you out there. But I'm just showing you why you can get to 3. Okay, so that's going to be 3 then. Add t log 10 of b. And then I can substitute this point in because now I have t and log 10 of v. So I know that t is 10, so log 10 of v is going to be 2.79, okay? Therefore, 2.79 is going to be 3 at 10 log 10 of b. That now I need to solve this for b, right? Um, the first thing I'm going to say is about 10 log 10 log 10 of b. Lots of tens. 10 log 10 of b. That's going to be 2.79 minus 3. And that's going to be minus 0.21. Then I can divide by 10 to say log 10 of b is, if I divide by 10, you get minus 0.021. Then again, I can solve for b now by taking tens on both sides. So 10 log 10 to the b, and again that will be just b because again the 10 will cancel the log because it's a base of 10. And so you're left with b will be 10 to the minus 0.021, which should be what is it? 3 significant figures here. B would be 0.953. The 3 sig figs, okay. Cool. So now we found V. We know A as well. We know B. Then it said to find a complete equation for V. Now, what that means is we need to rewrite the equation, but plug in our missing numbers, right? So A is 1,000, everything here. So 1,000 B, which was 0.953. Oh, let me write to the T, and that would be your model. Okay. Okay, cool. Then we are given exactly 2 years after it was bought. The value of the phone was 320. Use this information to evaluate the reliability of the model. So this is very typical, right? They give you some other piece of information, and then you need to substitute that into the model to prove how reliable or close it is to the true answer. So the value is 320, and T is 2. So you can do two things. You can either plug in 320 with V and then solve for T, or the far better way, 'cause then you have to take logs, right, or whatever. You can just plug in T 2, and then you just get V straight away. So T is 2, that means V would be 1,000 of 0.953 to the 2, and that would be it's T in years, by the way. I need to check this, by the way. Yeah. Oh. T's in months. There we go, because I got an answer of 907. That's not particularly right. See, I need to check the question there. Yeah, so with this modelling, what you should always pay attention to is the units, right? So T, you need to check them, it's in months. This is in years. So that means T is 2 years. No, sorry. T would not be 2, but 2 years is equal to 24 months, right? So that means T is 24, and that's what you substitute it in. So 24. There we go. So 1,000 of 0.953 to the 24. That gets you a lot of a more sensible answer of 314.94. Okay, in pounds. So that's our answer. But actually, it's very, very close to 320. So I think it's quite reliable, right? You can calculate percentage error if you wanted to be really sure. So you could say, well, again, so 314.9294 times our multiplier, so a percentage, increase or decrease. It's a percentage error, right? That has to give 320. X would be 320 divided by the answer, which should be 1.016. Therefore, times by 100, it'd be a 1.6 percentage error. Okay, that's very, very. I think that's very good. Really, less than 1% error. No, not less than 2% error. Sorry. Stats in significance level, for example, like you used to 5%, 10%. That's basically the error of margin, right? And normally, if it's below 5%, you accept, you know, the like null hypothesis. Here, because it's like below 2, you can kind of accept it's a good error. So it's a good reliable, it's a good approximation, right? You don't have to put the do percentage error. You don't have to do that, right? I'm just showing. You can be really, if you feel a bit like I need to be a bit more rigorous or precise, you can do it that way. But in general, notice it's really bloody, it's really close, isn't it? So the answer is yes. And the thing is as well, you really have to be, you have to appreciate with these modelling stuff. It's not perfect, right? You're not going to get perfect answers. You're not going to expect your answer to be between like 319.99p. Okay, you have to be a bit more open-minded than that in reality. Um, so an answer close like this is still pretty good, right? Um, Only when you get to say something, I don't know if it's like 200 or something, then it's a bit off, right? It's not as reliable, but because it's only a few pounds off, it's not a big deal. So you kind of have to be a bit. You shouldn't be stringent with these type of things, right? As long as it's in the ballpark, and you're not too pedantic, essentially, about how close it is to the answer. You have to take that into account. So because it's not really that far away, it is a good approximation, right? So uh, the model, therefore, is reliable. So reliable, obviously, again, doesn't mean it has to be like perfect. It doesn't have to be spot on or like off by like a decimal point. It just has to be reliable. So you can use it to get like a sort of ballpark figure, right? Which is what we got here. So the model's reliable as it predicts the value to be 314.94, which is close to 320, right? And that's essentially your reasoning, okay? Actually, funnily, I did check the mark scheme as well. And actually, they do not accept in this particular case if you say no. Okay. Normally, they do say you can have yes or no depending on your reasoning, but here they've said straight up you can't say no. You have to say it is reliable. Again, so it's saying like you do have to be quite open-minded and flexible with how different the answer is. You know what I mean? So you can't say I was off by like a decimal point, so therefore it's not reliable or whatever like that. You do have to be quite. And the examiners expect you to be fairly open-minded with your answer. Okay. But yeah, so that's really all it is. So again, the main central point, again, if you get a question like this, you just need to take logs, okay? If and an equation like this, if you have a graph that's in logs, because then if you have it in logs, you can then substitute any points of information you're given. Because remember, this is v, but this coordinate only works for log 10 of v when v is logged. Okay, so you have to take logs first, and then you can substitute the points in. Okay, cool. Question 6. Okay. How many questions I put in that? 15. I think some of it might be on to the next session, I think. Anyway, question 6. So, again, this is very typical. Every year you get like a sort of first principles question. I think most people like it, right? But again, it's better to go over it. Either they can give you sine or cos, or they will give you some sort of like x squared, x cubed plus 1 or something like that. Some sort of like polynomial. But probably in the harder cases like sine and cos, and that's what I've got here. So we're given y sine x, and we need to show the derivative is cos x by first principles, and we're given this information here. Usually we'll give you this, right? You can sort of see it. By the way, I'm not going to go too much into it, but if you essentially use, and this isn't a proof, but if you use small angles, you should know sine theta goes to theta. So then that's essentially saying sine h over h goes to h over h, which cancels to 1, which is what we've got here. Because remember, h has to be small, theta has to be small. Likewise, with cos h, that would go to 1 minus a half h squared. But then in here, cos h would be 1 minus half h squared. But actually, h squared, when h is at 0 pretty much, this will pretty much be negligible. That will go to 0. So you're left with 1 minus 1 over h, which is 0 over h, which is 0, right? Which is why we got that result there. That's not the proof, but you can use it to help you see those. But they will give you the results, right? But I'm just showing there they don't come from nowhere. Okay. Hopefully you're a bit comfortable with that now, and obviously the double angle which I've got here. Anyway, so that's just the waffle they give. So let's do it by first principles. So again, the first principles formula is given to you in the formula book. You don't have to remember it, but like with all formulas, you need to know how to use it. Okay. So that's our first step. So say if we call this f dash, not f of x, sorry, to make it match this, right, the f dash. Therefore, by using the formula, I can say f dash of x then it's going to be lim, which means limit as h goes to 0, of f of x plus h minus f of x over h. Okay, and then I just substitute it in. So the input x goes to x plus h, so that would be lim as h tends to 0 of sine of x plus h, and then f of x is sine x, so minus sine x over h. By the way, it's just a good idea to put the lim here. Make sure you don't forget it. I think it, it's hard to say if they're going to be lenient and stuff like this. If you say forget your lim h tends to 0 somewhere. But it's a good idea to just write it, right? It's only a few like words, really. I don't know, but it's best to be safe, right? Anyway, so let's do that. Okay, so how am I going to approach it then? What can I do now? Well, in a way, the question gives you a bit of a hint. Sine A plus B means we're going to have to do something with double angle. And I got a double angle. Well, not a double angle, but I've got an addition and of two angles here, right? And so I'm going to expand it. I'm going to use this identity, which is in the formula book, right? And I've quoted it here. Sine A plus B, which is this, right? Here I've got sine x plus h. So let's write lim as h tends to 0. X plus h, if I almost put an x and h here, that's going to say sine x cos h, right? Plus, because if it's a plus here, it has to match the plus here, right? But the cos one, I think we go over cos one now. I'm going to leave that till the later question to explain that. But then it'll be cos x, right? Sine h. And then I'm going to, oh god, I don't have much room here. I'm going to rewrite it actually. Let's move it over here. That will be lim as h tends to 0. Sine x plus h will go to, as I said, sine x cos h plus cos x sine h. So all I've done here, by the way, is replace the a and the b in the formula with x and h, right? Then that's minus sine x, which we have here. And then that's all over h. Okay, so what do I do then? Because I can't really just cancel stuff out immediately. So I'm gonna have to do something. You're gonna notice I can factorize. So, I noticed I have two sine x's. Tends to 0. Sorry. So that's sine x, and I notice that'd be cos x, cos h. Sorry, and then a minus sine x would be minus 1 over h. Plus sine h cos x. I can't do anything with that, right? But that's the best I can do to factorize it, right? To simplify it. Then what I can do actually, like with fractions in general, really, I can split it up into two. So I can split the limit up as well. So then I can say limit h tends to 0 of sine x. Oh, it won't let me delete this. What's going on? There we go. I don't know what happened there. Cos x, sine x, sorry, of cos h minus 1 over h. And why am I splitting it here? Hang on, let me just split it here. Over limit h tends to 0 of sine h cos x over h. And I was saying now, why have I split it up like this? Well, I notice I have a cos h minus 1 and a sine h here. So I have a cos h minus 1 and I have a sine h on this side. So I'm going to want to split it up to use both of oh god, to use both of the results, right? That's what I'm doing here. Oh, sorry. And that's what I'm going to do. So now I can basically almost effectively substitute this in. So then, lim of h tends to 0 of sine x times by cos h minus 1 over h, which is here. So remember, h is going to 0. That's what this limit's doing. So as h tends to 0, this bit goes to 0. So that'd be times it by 0. And then lim as h tends to 0 of, well, sine h over h would go to 1. So that means it's 1 times cos x, right? Uh, there we go. Okay, cool. So I've used that, and actually we've got pretty close to the answer now. Well, zero. Well, 0 times anything will go to 0, so that's 0. And then you're left with this. Lim as h tends to 0 of cos x, essentially, right? Then get rid of the 0. But what's going on here is I'm changing h, aren't I? I'm saying h changes and goes to 0. But here I have an x. X is not related to h. So actually, I can just get rid of this limit now because changing h won't change this at all. So this will just be left to cos x, right? And that is your f dash of x, which we wanted to prove, right? So that's saying then, therefore, the derivative is cos x, right? Well, y sine x, and we've done it. So that's the sort of idea, right? So really, once you got to this point, you just expand it using the addition formula. Then you kind of try and factorize to get these two, and then just substitute the results in. Okay, cool. Hopefully that shouldn't be too bad. Okay, now we have question 7. And it's a quadratic modeling question, right? So what we're told. So again, we're given some information. I'm just going to note the variables, right? H meters, vertical height, and horizontal distance x meters. Okay. And I can see that here, x and h. Okay, so that's really the information. These bullet points here. So the balls hit from a point on top of the platform of a vertical height of 3 meters above the ground. It reaches a maximum vertical height, horizontal distance of 90. And the vertical distance of 27 meters, the horizontal distance of 120, actually. Oh, want to make it a tad bit clear. There we go. Okay, then we are told down here, given also that h is models of the quadratic function of x, I made that bold. Find h in terms of x. So this is again very typical. So you need to basically give give the formula for this, right? And it's a quadratic curve. So what's a general quadratic like going to look like? Right? H of x or h, let's just call it h. Well, it's going to look like ax squared plus bx plus c, right? And hopefully you can recognise that's a generic quadratic expression, right? So that means any function, any quadratic function has to look like this. Hopefully you can see that. That's basically kind of the main step, essentially. To realise you can just give a generic one, and then our mission is to just find A, B, and C, right? To find a complete model. Oh, didn't mean to delete it. I want to get rid of the underline bit. And that's what we're going to do. And we're going to use this information here. Firstly, we are given it's hit from a point on top of a platform of vertical height 3 meters above the ground. So that's kind of saying at the start, right, at this point here. And they've given it here, so h is 3 here. And that's when x is 0, right? So when it hasn't moved at all, it's at a point of 3 above the ground. So if you formulate this in maths, that's saying, well, x is 0, h is 3. So actually, let's substitute that in then, see what we can do. So that's saying 3. Well, if we substitute that's going to be a of 0, right? And b of 0, but subbing x is 0, add c. Well, that goes to 0 and 0, so that means c has to be 3. So therefore, we can rewrite our model to be h is ax squared at bx, and now we can add the 3 in. Cool. Now let's do the other bit of information. Then we'll say it reaches a maximum vertical height. Remember, h is vertical height after traveling a horizontal distance of 90. So we are saying when x is 90, h, not giving us the height here, but h is h max, right? So h is this maximum height, h max. How are we? What does that mean then? Well, there's two ways of approaching this. You could complete the square, because obviously we should know completing the square and a quadratic gives us information about the maximum, right? But I actually think it's going to be a bit messy to do it. What you could realise instead is actually we can differentiate, right? Because h max is a turning point, so h max obviously will correspond to the maximum, which is this sort of turning point here. So that's h max, and that's going to be obviously when x is 90. If we, it's going to be the turning point, so we could say dh by dx is going to be 0, right? So then we can differentiate it. But don't be afraid of the constants, right? dh by dx then. So differentiate x. So x squared will go to 2x, and then a would mean 2ax, right? Then b, well, x will go to 1, so it just be b. Okay, and that has to equal 0. But we also know that this occurs when x is 90, so we can substitute 90 in. So say 2a of 90 add b equals 0, but therefore 180a equals minus b, right? Because 2 times 90 is 180, 180a, then I move the b on the other side. Cool, so that's we've got one equation. Let's see what we can do with the other bit of information then. Maybe we get another equation to solve this, okay? Then we're given the vertical height of 27 meters above the ground. At the horizontal distance 120. So that's going to again be x is 120, h, the vertical height is 27. So that means h equals 27, x is 120. Therefore, if we substitute it into, again, this sort of generic quadratic expression we got, we can say 27 is going to be a of 120 squared add b of 27, no, 120, that's 120, sorry. add this 3, okay? And actually then I can just put these values into the calculator to simplify it a little bit. So 27 is equal to, well, 120 squared is going to be 14400A, and then 120B. And then add 3, but obviously I can take 3 away from both sides, so that'd be 24. So actually then I've got 2 equations to solve for A and B. These are simultaneous equations, right? So I can call that equation 1 and 2. Um, you could. Some mark schemes are quite finicky, quite fickle. Sometimes they let you just pull it into the like simultaneous equation solving your calculator, and they'll be fine with that. But I do think you should play it safe, especially for 5 marks. Here, uh, just try and not solve. You know what I mean? Solve it manually. Yeah. If you are really struggling for time, then just put it into the simultaneous equation solver and move on. You probably lose that most amount of mark right for showing you're working. Um, but I think to play it safe, you don't know what the mark scheme's going to be like. Sometimes they accept it, sometimes they don't. But here it's just best to solve it manually. But here we already know an expression for b. So b is going to minus b is 188. So that means b is going to be negative 188 by dividing by minus 1. So then I can substitute 1 into equation 2, right? To then get 24. It's going to be 14400A. Add 120 of b, but b is minus 188. So then that'll be 14400A minus, well, 120 times 180 gets you 21600A is equal to 24. I can simplify this, can't I? So 14400 minus 21600 is left with. Okay, we're back. I think we are. Yeah. So apologies about that. But what happened was I was in the middle of computing it with putting in a calculator, accidentally flung it into my laptop, and then that caused the laptop to just crash and reset because it's. Oh my god. Yeah, my laptop's very run down and sensitive. I don't know. I just noticed in some of the streams it gets a bit laggy towards the end because the laptop just can't process dealing with stuff and it's just quite run down. But yeah, that's oh my god. Okay, and what I'm gonna see is because at the moment it's 2 different streams, but for YouTube or whatever, I'm gonna see if I can combine it into 2 so there's not much of disruption. But either way, there's gonna be a bit of a gap between obviously what happened. But yeah, anyway, let's just get on with it. So 14400, I'm trying to fling it on my laptop now. Minus 21600A gets you minus 7200A is 24. Then I could just divide by that. So 24 divided by minus 7200 gets you A is minus 1 over 300. That does not have a nice decimal, so you have to leave that in exact form. So that's A. Therefore, B. Remember, B was. Oh, did it not write B anywhere? Oh, did it not save that part? Oh no, B's here. Sorry, B's minus 180A, so B's going to be minus 180 of A, which is minus 1 over 300. And then that's going to be 300. That's 2, doesn't it? 300. And that's going to be 3/5. Quite nice, right? So therefore we found A, B, and actually we found C earlier. So therefore put off, if we have to find H in terms of X, so the complete model, like you should be drilled into your head now with these sort of questions. You have to restate the equation again with the missing values. So A is minus 1 over 300 x squared plus B, which is plus 3 over 5 x. And then I think C was what was C? We did it up here. C was 3. Okay. So that should be your complete model. And it's very typical with modeling to get weird numbers like this, okay? That's okay as long as it's not too weird. Like if I got some mad like third decimal, then I've probably gone wrong somewhere. But here I've got a fairly nice fraction. But yeah, that's that for 5 marks. Cool. Then part B says firstly again, this is pretty typical to sub some values into your function to get some back. So firstly, the maximum vertical height. So you could think, well, differentiate it, set to 0, find x and h, but they already told us that the maximum vertical height here, the second part here, occurs when the horizontal distance, when x is 90. So really, we just have to plug in x is 90 in without having to do any differentiation or complete the square or anything like that. So when x is 90, h is minus 1 over 300 of 90 squared, add 3/5 90, add 3. Um, and that will be 30. Quite nice number. There we go. 30 meters. Okay. And then the second part says the horizontal distance travelled by the ball. So horizontal, remember, is x. When it from when it was hit to when it first hits the ground. Okay. So remember, hitting the ground is going to be when the vertical 0. So it's going to be the x the root, right? The x intercept, which again is fairly common to use the model to find the roots, right? So here the first when it first hit is 0 here, x is 0. Then we need to find this missing value of x, and so the distance will be this x minus 0. Well, it's just going to be here. Anyway, so we need to find the root. Um. So then we You can, again, like I discussed earlier, you could put it into the calculator, but if you want to be really safe, the best thing with this, instead of putting in a quadratic solver, you can kind of do both. So just use completing the square, which should be fairly quick. So x is going to be minus 3 over 5, plus or minus the square root of 3 over 5 squared, minus 4 of minus 1 over 300, 3 over 2a. Which is 2 over 1 is 1 over 300. So you just quickly write down the quadratic formula so you don't have to bother with factorising or complete the square or anything. But then you can pull it into the quadratic solver, right? Because then that'd be the same value, right? But then you technically shown how you got your answer, right? Um, but yeah, let's do it. So minus 1 divided by 300. 3 divided by 5, 0.6 and 3. You get 184.8683 or at minus 4.868 But obviously you can't have a negative because it's a distance, right? But x has to be 0, so positive. Hence, horizontal distance. Does it say to what one to round it to? Give your answer to the nearest meter. So obviously that's in meters. So round it to the nearest whole number. So that's going to be 185, right? To nearest meter. Okay. And then what's part C saying? Um, the possible effects of wind or air resistance are two limitations. The model give another. Oh, this makes me laugh because I know every single time, and I'm a culprit of it. Everyone just loves to give air resistance as the limitation always, and it is fair. But I love that they just took that away from you because they're like even the examiners are so sick and tired of seeing everyone write air resistance. So you have to come up with something else. But actually, the other way thing you can always say is the fact that you can say, well, it's a flat surface, right? The ground is flat. But it's that in real life, it's not going to be exactly flat, right? It's going to be a little bit hilly. It's going to be like some, I don't know, like stumps or something like that. Like it's going to be quite elevated, and then you know, what I mean, then it'll dip down slightly. It's not going to be completely like flat, is it? Really, if you think about it, it's going to be like bumps and here and there. It's not be completely level, and that's your limitation, because then obviously that could affect where it hits when it hits the ground, because obviously the ground will vary at height and stuff like that, and it varies the maximum. It really does affect the values of the model, right? If it's not a completely flat surface, that is the limitation, and that is another one you can pretty much always copy in, because obviously it's very very hard to model the x-axis, which is going up and down. So you just model it as flat. But that is a limitation, right? If they will not let you say it's air resistance, then you can say that. So limitation, it's just funny that was. Limitation is uh, the ground, or the horizontal ground, I'll just say more specifically, uh, would not be perfectly flat, right? In reality. Uh, and that's really what to say, really. And then that would affect, like I said, the values, right? And then that would actually affect the way you can actually model it as a quadratic. So it is a limitation. Okay. You could say something really like, I don't know. I did see. I remember the mark scheme as well. You could say, would it be modelled as an exact quadratic curve? It might seem a bit obvious, because obviously, again, because of things like air resistance, it's not going to be like a nice curve, like symmetrical curve like this, right? Um, and also you could comment on the fact it could be like multi-dimensional, so it could be 3D, because this is assuming it's a 2D thing as well, because it's only X and Y. But obviously, in reality, it'd be like three different variables. You don't have to think about that really. Just that you can talk about air resistance and the fact the ground is completely flat, right? Those are the two typical limitations. Anyway, let's move on. We're on 10:30 now. Okay. Uh, okay. Now with this, some binomial expansion. Again, this comes up every year, pretty similar. Um, okay. So it says find the first four terms of the binomial expansion of root 4 minus 9x. And essentially that is actually using this formula here. This is the AS version, but this only works when n is a positive integer. So this little n here at the end, this n here, means the natural numbers. So 1, 2, 3, 4, which just means positive integers, whole numbers, right? But obviously we're going to have a surd and stuff, so it's going to be fractional. And pretty much always, at least for A level, you're going to have to use this formula, okay? But that's really all we're going to do. It's just formula work. But if we're going to use the formula, we're going to need to get it in this form here. 1 plus x to the n. So we need to get this third in terms of that. Well, how are we going to do that? Well, we are going to, just use third index laws, right? So you can say root 4 minus 9x is going to be 4 minus 9x to a half. Uh, and then we're pretty similar, right? But um, it has to be 1 plus x, not 4 plus some lots of x, okay? So we need to deal with this 4, okay? And the way you're going to do that is factor it. No, actually, you don't have to be freaked out with it. I think some people may be a bit freaked out. There's a half here. How can I factor all that out? But really, keep the half in, keep the bracket in, then factor the 4 in the middle of the bracket before you take it out. So that's going to be 4 lots of 1 minus 9 over 4x, okay? Hopefully you can see that right. Let's do it step by step here. So I've not considered the half yet. I've just factored it inside the bracket to almost create two brackets. Okay, hopefully you see that step. Then I can factor it out by using this index law here. A to the mn is times in the powers together. But really, this is 4 to the power of 1. So this is saying 4 to the half then. And then this in the bracket, 1 minus 9 over 4x, is also raised to a half, right? Because it's almost like saying ab to the n is going to be a to the n, b to the n, where we have a product here. So the product here is 4, and this bracket here, 1 minus 9 over 4x. And all of that is raised to the power of a half for n. And so really, what this law is saying here, we can just split and we can distribute or spread out the power between the two products. And that's all we've done there. Okay, so actually, when you split this up, instead of trying to do it all in one go, to just factor the 4 out like this quickly, if you are struggling, you can do it step by step like this, and hopefully it should be a bit clearer. Okay, but then we can simplify this. 4 to the half is 2, right? Again, if you're unsure, use the calculator to check. That's our 2. Did I say half? I said 2. I meant to. I don't know why I said that. The halves everywhere. Anyway, 2, lots of this. 1 minus 9 over 4x to a half. Now, this is in this form here. Because now we could say, if I call this big X over n, then big X is going to be minus 9 over 4x. Hopefully you can see that. If I substitute that in, I get this same bracket here. And I can call n as a half, which is this index here. Then if I substitute these two into here, this formula here, then I get my expansion, right? So I'm going to ignore the 2, then I'm going to apply the expansion to this bracket here, because then I could just times by 2 at the end. Anyway, so let's do that. So the first term is going to be 1. Then the second term is going to be nx. So plus n, remember n here is a half. And then x is going to be here. So this x part here, minus 9 over 4x. Okay, not x, but minus 9 over 4x. Okay, hopefully you can see that. Then we have the next term, which is going to be n of a half minus 1 over 1 times 2, which is 2. So this is a product, by the way. I'm times in n by n minus 1. Okay, and then x squared. But remember, x is minus 9 over 4x. So that's going to be that squared. And then I need those are 3 terms, but I need 4 terms. Okay, so that's 1, 2, 3 terms. I need a 4th. So I'm going to continue on with the pattern here. So then it's going to be n times n minus 1. Oh god. Yeah, see, it's starting to get slower now on my laptop. Half minus 1 and a half minus 2. Okay. And that's going to be 3 times 2 times 1. So that's going to be 6. And that's going to be x cubed. So it's going to be 9 over 4x all cubed. Okay, and that's your formula there. If you are unsure here as well with exactly what that would go to, notice this is the generic term x to the r, but you're going to want x cubed, right? So clearly r is going to be 3. Then you basically just substitute r is 3. So that's going to be n, for example, the top bit, n minus 3 plus 1. So that's going to be n minus 2. So you times in one n to n minus 2, which is what we've got here, okay? Likewise on the bottom, r would be 3. So it's going to be 1 times 2 times 3, which is what we've got there. So if you are a bit unsure, if you need to go to higher powers, you can again just use the formula to spot what you need to do. But anyway, it's so slow now. And now we just simplify it all, right? You can use the calculator to do this, so it's going to be 2, if it lets me. 2, lots of 1, and then I'm going to simplify the first bit, so a half times minus 9 over 4 is going to be minus 9 over 8. So it's going to be plus, well, minus 9 over 8 x. So I'm dealing with all the coefficient parts. Then for the next x squared term, it's going to be a half times a half minus 1. But then it's also going to be times by minus 9 over 4 squared. Why? So this bit here, because, again, like I did previously before, just minus 9 over 4 x squared, or x all squared, sorry. I can, again, spread the power out. So minus 9 over 4 squared, x squared, okay? So then that's the coefficient part. And that minus 9 over 4 squared can then be multiplied by everything else on the left before it. Okay. So the half of half minus 1, then it's times by the minus 9 over 4 squared, divided by the 2. And so the coefficient for x squared is going to be minus 81 over 128 x squared. And then for x cubed, it's going to be then a half of a half minus 1 of a half minus 2. And then it's going to also be times by minus 9 over 4 to the cube, right? Power 3 over 6. And so the coefficient of that would be minus 729. We'll get rid of that. About 1024x cubed. And that's our expansion. So then we just times by 2 to then say it's 2 minus 9 over 4x. So just times everything by 2. Times by minus 81 over 128 times 2. Might that be minus 100, minus 81 over 64x squared minus 729 over 1024 times 2. That would be minus 729 over 512x cubed. And that's your expansion, right? So that's saying that the square root, well, the original, so the square root of, what was it, 4 minus 9x, which obviously was a half, no, it's 2. That's of 1 minus 9 over 4 x to the half. And that's going to be approximate to this. Because remember, this would go on forever, but those were the first 4 terms. But there are more terms, so this is just an approximation, okay? But yeah, cool. So then part B. So what's part B saying? Then it says a student uses his expansion of x is 1 over 9 to find an approximation for root 3. That's a fairly common thing, right? Again, to substitute it to get an approximation for something. Then it says using part A without doing any calculations, state whether the approximation would be overestimate or underestimate for root 3. Given a brief reason for the answer. So what's going on is I'm plugging this value of x in, but you shouldn't plug it in because it said do not do any calculations. So we just have to stare at answer essentially. Let's say, why has it moved? There we go. I don't know. But what's going on here is it's basically saying if we use this 4 terms, would it be an overestimate or an underestimate to the true answer for this, right? Because remember, we only got the first few terms, so it's just going to be an approximation of the true answer for this square root bit. So here, say this is root 3 for x is 1 over 9. If we plug in x 1 over 9 to the first 4 terms, that number it gives us is going to be an approximation, but is it going to be above or below the actual answer for root 3? Well, really, again, like I said, it said just use the answer to just look at it. So, what do I see really happening? So, because I said it's the first few terms, what would the next few terms look like? What would the other terms look like? Because obviously then that would be the actual answer if we added all the other terms. Well, I noticed we have 2, but then it's minus x, some lots of x, minus some lots of x squared, minus some lots of x cubed. So we're actually minusing some amount each time, aren't we? So that's going to be minus k lots of x4, then minus k2 lots of x5, so more constants, some multiple of x5, some multiple of x6. So we're subtracting each time, aren't we? Because we're always subtracting. And that trend would continue, right? And you can kind of see that so if you're not entirely convinced because of the fact. Notice again, if we have an even, notice, say, with times in n by n minus 1, n minus 2, that's going to be even, and then all of these are going to be not even. Sorry, that's going to be positive. Then all of these are going to be negative because the half minus 1 is negative, half minus 2 is negative. But if there's an even number of what's it called? If there are an even number of brackets here, so it's going to be positive then negative, positive then negative. Uh, it's going to be negative, right? For example, with the x squared term here of let's go up. Oh, for God's sake. Say we have 2 brackets here, so the even number of brackets of products. We got a positive on the negative, so it will go to a negative. But when it's even, this is an even power of x. So that means if it's minus 9 over 4 squared, that's going to be a positive number because it's an even. Likewise, on the other side for odd, again, we're now going to have an odd number product. So this is going to be positive. Again, look at x cubed. This goes to a positive coefficient because 2 positive and 2 negatives, they give a positive. But this then would be an odd power of a negative, so it's going to be a negative as well. So overall, all the coefficients, what I'm saying is, that's the kind of rigorous way of looking at it. But all the coefficients are going to be negative, and without having to go into that, you can just immediately spot it, right? But I'm just again giving like the full explanation behind that. But it's all negative. And actually, that means any further terms are going to be negative as well. So that means actually our true answer would be smaller, right? Because it would include more negative terms. Um, and obviously x is positive, so obviously whatever you plug in x will be positive. So negative times positive will be negative. So actually this will be an overestimate. So our approximation or our expansion, if you will be an overestimate because um, uh, the expansion involves negative terms of x, right? So less terms means a less negative answer, right? Hence an overestimate. Okay. Hopefully that made sense, right? But that's sort of the thing you got to get at. Okay. I think that's it for this part. I did split this up into 2. actually, because the next part is here. To look at the other questions. I thought I was gonna do more than that actually, but I don't know. There's been a little bit of a calamity, especially what happened earlier, my laptop breaking down. Uh, but actually, I guess it's quite fitting because I don't have more time sadly now. But I can do this part 2 in the next session, right? Um, because this goes from like question 19, question 9 to like 16, I think. That I took, so it's based like a past paper essentially, which is quite fitting because it's all the paper topic questions that weren't in paper 1, and I've made a whole paper worth of other topics. So this could resemble quite nicely paper 2. I don't know. Oh, it'd be good practice anyway. But yeah, that's half of the questions done. We'll look at the other half next time. Hopefully, it goes a bit smoother. um, but yeah, but that'll be Monday, I believe. The next time, but then I'll be doing it on Wednesday for the night before, where I'll pick certain high priority questions, right, like I did last time. Which I hope was useful, by the way. For those who tuned in to that video or whatever. But I should be doing the same again. But yeah, so that's the first part of this done. We'll tackle these questions um, next time. I guess I'll show them, right? But if you want to be a bit, obviously see this question here. But if you want to see like, if you want to be like a bit like, what's it called? If you want to see the questions fresh next time, obviously look away. But I don't know if you want to practice beforehand, obviously, or whatever, and then you want to tune in and see me go over a particular problem. These are going to be the harder questions, by the way, because these are going to be like towards the end of the paper. So obviously the earlier questions are going to be mostly easier. So these are going to be harder next time. Obviously, again, to reflect the paper. But if you want to practice it, go ahead and then obviously tune in next time or whenever. Obviously, then do whatever you want with it. Then go ahead. Uh, but yeah, I'm gonna leave that there then after this. So I'll try and publish this onto YouTube again. I'm gonna try and combine it because at the moment I've got 2 different streams because of the fact my laptop crashed. So I'll try and find a way to combine it so it's not disruptive. I don't want to split it up into 2. Parts today anyway. But this will be a 2-parter anyway, as I said. I'm going to stop waffling now, so I'm going to leave that there. But yeah, I'll see you next time. I'm going to do the next part of this, okay? But yeah, see you next time.